Hello everyone. This video is about the methods of excitation of DC machine. The DC machines, they are broadly classified into separately excited and self-excited machine. They are classified on the basis of the methods of excitation. So we can call either the methods of excitation of DC machine or types of DC machine. So in separately excited DC machine, there is no electrical connection between the armature winding and the field winding. Both are electrically isolated from each other. In self-excited DC machine, the field winding and the armature windings, they are electrically connected. And for self-excited DC machine, we don't have to give any separate excitation to the field winding. Self-excited DC machine can be further classified as shunt machine, series machine, compound machine. This classification is based on the way in which the field winding is connected. In shunt machine, the field winding is connected in parallel with the armature winding. In series machine, the field winding is connected in series with the armature winding. Compound machine will have both the shunt and the series field windings. Compound machine, they are further classified as long shunt and the short shunt compound machine. Both long and the short shunt compound machine, they are further classified as cumulative and differential compound machine. So these are the classification of DC machine. Now, before going into the classification and before going into the equivalent circuit of types of DC machine, we need to know the concept of back EMF. We know that the armature winding is rotated inside the magnetic field produced by the field winding. By Faraday's law of electromagnetic induction, when a current carrying conductor is rotated inside a magnetic field, an EMF will be induced in the conductor. So EMF is induced in the armature winding by Faraday's law of electromagnetic induction. Now, the direction of the induced EMF will be opposite to the cause which is causing the EMF by Lenz's law. Hence, the direction of the EMF which is induced in the armature winding will be acting in the reverse direction to that of the armature winding, armature voltage. So this EMF, it is called as back EMF since it is opposing the armature voltage. So back EMF can be calculated by using the formula EB equal to phi Zn by 60 into P by A, where phi is flux per pole, Z is number of armature conductors, N is the speed of the motor in RPM or speed of the rotor in RPM, P is the number of poles, and N is the number of parallel paths. The number of parallel paths A will be equal to P for lap winding, and it will be equal to 2 always for wave winding. Now we are going to see the equivalent circuits of the separate DC machine. This is the equivalent circuit of the separately excited DC machine. As already told, there is no any electrical connection between the armature winding and the field winding of the separately excited DC machine. So this is the equivalent circuit of the DC motor. So here the V represents the armature voltage, the voltage, DC voltage, which is applied to the armature winding, and Vf is the voltage that is applied to the field winding. So with the help of the supply voltage V, an armature current Ia will be flowing within the circuit of the armature, and a back EMF of Eb, it is being induced in the armature winding. And Eb is given by phi Zn by 60 into P by A. And we can write that the back EMF by using the KVL equation applied within the armature circuit. So Eb can be written as V minus Ia Ra, where Ra is the resistance of the armature winding. And from this equation, we can write Ia is equal to V minus Eb by Ra. So this is the equations of back EMF and the equation of current, armature current of this circuit. Now we can see the self-excited DC machine under which we are going to see the equivalent circuits of shunt and the series machine. So this is the equivalent circuit of the shunt motor, wherein the field winding, it is connected in parallel to the armature winding. So the voltage we are having the supply voltage, DC voltage, which is being applied across the armature winding. Since the shunt winding, shunt field winding, it is connected in parallel with the armature. The same voltage we also will be appearing as the supply voltage across the shunt winding. Construction wise, we can see the difference between the shunt winding and the series winding. We can see that the number of windings on in the shunt field winding will be more, and the thickness of the winding will be less. The thickness will be less for shunt field winding. And if we see the series field winding, the number of windings is less for series field winding, and the thickness of the series field winding will be more when compared to that of your shunt field winding. Why? Because this has to carry the armature current. So resistance of the series field winding will be lesser when compared to that of the shunt field winding. So this is the shunt motor equivalent circuit. For this shunt motor, we can write the equations back EB equal to V minus IARA by applying the KVL equation within this loop, armature loop. And IA can be written as V minus EB by RA, where RA is the armature resistance. And we can also write the armature current as the difference between the total current coming out from the supply voltage minus the shunt field current. So IA can also be written as I minus ISH. For series motors, this is the equivalent circuit. Here, the series field winding is connected in series with the armature winding. Now we can write the back EMF equation here as V minus IA, since IA and the series field current and the supply current all are connected in all are same because all these are connected in series. So EB will be equal to V minus IA into RA, that is the resistance of the armature winding, plus RSC, which is the resistance of the series field winding. Now we can write IA equal to V minus EB by RA plus RSC. So these are all the equations which govern the shunt motor and the series motor. Now we can see the compound motor, which is also one of the classifications of self-excited DC motor. So this is the long shunt compound motor, and this is the short shunt compound motor. In the long shunt compound motor, the shunt field winding will be connected in the series connected in the parallel with the series combination of the armature winding and the series field winding. That is, armature winding and the series winding both are connected in series first. The series combination will be connected in parallel with the shunt field winding. So this is the long shunt compound machine. And for the short shunt compound machine, the shunt field winding will be connected in parallel with the armature winding first. The parallel combination is connected with the connected in series with the series field winding, which these combination will be connected across the supply voltage. This is the short shunt compound machine. Now, these two machines can be either acting as a cumulative compound machine or a differential compound machine. In a cumulative compound machine, the both series field and the shunt field will be aiding with each other. That is, the direction of the shunt field and the direction of the series field will be aiding with each other for cumulative compound machine. And for differential compound machine, the direction of the shunt and the series field will be in opposite to each other, will be acting in opposite to each other. So both shunt or the both long shunt or the short shunt can operate as a cumulative compound machine or a differential compound machine depending upon the directions of the shunt and the series field direction. That is shunt field flux, and the series field flux. If they both act in a direction such that both aid each other, then we call the machine as the cumulative compound. And if both are acting in opposite direction to each other, then we call that as the differential compound machine. So we have seen the excitation, methods of excitation or the types of DC machine in this video. Thank you.